Okay, in this module we've been talking now a great deal about these subatomic particles. We talk about protons that are positively charged and exist in the nucleus. We talk about neutrons that are neutrally charged and also exist in the nucleus. And then we mentioned these electrons, which are much, much smaller than the first two. They're protons and neutrons. But they don't exist in the nucleus. They exist out away from the nucleus. And also understanding that they're negatively charged. So if we take an atom and we have what we would refer to as a neutrally charged atom, that means we have to be able to be neutral. Because I've got pluses, well those aren't neutral, the protons, and I've got minuses, those are the electrons. And both of those things individually are not they're not neutral. One's positively charged, one negatively charged. But what if I have an equal number of each? What if I have 5 pluses and 5 minuses? Therefore, the pluses cancel the minuses and vice versa. So a neutrally charged atom is one that the pluses and the minuses are equal and opposite. And we're going to talk about that in more detail here in just a minute. But an important part of what we understand about electrons is where they are. And they exist out away from the nucleus. And we can get pretty deep into this when it comes to some of the chemistry concepts here. We won't, but we'll try and make it as simple as possible. But these electrons are kind of predictable about how many and where they exist outside the nucleus. There are some electrons that are very close to the nucleus, some that are further away, some that are further away. Now, the further away and the further away part does depend on the size of the atom, how big it is. If it's a big atom, obviously there's a lot of protons, therefore to be neutrally charged, there's got to be a lot of electrons. And so if only a certain number can be close, and then a certain number more can be the next and the next and the next, then that atom has to get pretty big. Well, those locations we refer to are referred to as the electron shells. And we talk about, well, how many electrons can exist in a shell? Well, it depends on the shell. So we number them. Shell number 1, shell number 2, shell number 3, shell number 4, shell number 5. We number them. And basically, if we give, and it's an equation that's actually in your packet, where if we give the equation of 2n squared with n being the shell number. Probably could have done the number sign there, but that's okay. So if n's the shell number, it tells me what is the maximum number of electrons that can be in that shell. So when we look at shell number 1, well, if the shell number is n, I plug 1 into here. 1 squared is 1 times 2, so there can be 2 electrons, maximum number of electrons in shell number 1. Shell number 2, okay, if I substitute that in, 2 squared is 4 times 2 is, there can be up to 8 electrons. Now this actually does give a reason for the shape of the periodic table that we'll describe a little bit as well. If we go up to shell number 3, now luckily when we're talking about the human body, most of the elements we deal with are up in this region, so they're a little bit easier to deal with, or at least close to those areas. But if we look at shell number 3, so 3 squared is 9, okay, and 9 times 2, there can be 18 electrons. And so you can see how that works. Now it does get a little bit crazy in terms of how do these atoms fill these shells. That, okay, we're going to put 2 electrons in shell number 1 because that's what shell number 1 can hold. And then we're going to put 8 electrons in shell number 2 because that's what shell number 2 can hold. But as we get up into those upper shells, there's some energy level differences that we don't fill shell 3 before we go to 4, before we go to 5. Okay? And as you get into a chemistry class, an inorganic chemistry class, they kind of teach you how those fill. But what we want to understand is those electrons. Okay, well, maybe this analogy works. Okay, you've been, let's say, you recently graduated high school. You've been living at home, or maybe you're still living at home. But you're living at home. Let's say you're in high school. So everybody's been in high school, okay, for whatever. It might have been the greatest year of your life, might have been the greatest 3 years of your life. But anyway, everybody's been to high school. So you go to high school, you're living at home. Obviously, you are then responsible for your household rules. Your parents kind of tell you how they want your haircut. They tell you how they want you to dress. They tell you how they want you to drive the car, what time they want you home. So you're under the control of your parents, and you're very tight with your parents. But let's say that you've decided, hey, I want to go to college or I want a job and I'm going to go to a distant place. I'm going to go to Florida. I want to go back east. I want to go overseas. You want to distance yourself from that control that you've been experiencing up till that point in your life. The further you are from home, the less parental control you experience. Because let's say, all right, you're living in Florida and your parents call and say, hey, you need to be home by 10:30 tonight. What? Okay? I mean, there's just no way you care at that point. I mean, you might think about it, just to laugh at them. But for the most part, you're going to say, yeah, 10:30, well, yeah, whatever. Things don't even get going here till 10:30. Okay? So they don't have that parental control they had before. So the closer you get to the control, now in this case, the nucleus, the more those electrons are basically out of use by any other element to form bonds and do some of those things. But you get out to those, what we call the outer shells. You get to the outer shells, and now, all right, we can use those because they're really not under control of that nucleus as much because they're as far out as we can get on that particular atom. So that becomes part of it. So you can't touch the inner electrons, the ones that are closely associated with that nucleus. Those electrons are loosely associated with the nucleus and therefore more free to come and go. They're easier to be influenced by other elements rather than the element itself. Thus, the outer shell really determines what that atom does. In other words, those outer shell electrons, whether or not they want to stay, whether or not they want to leave, whether or not they want to stay most of the time, okay, or a little bit of the time, okay, that determines the chemical properties of this element, of what it's willing to do with other elements. But the other element is influencing those outside, less controlled electrons. And because it contributes to those bonds, we refer to those as our valence electrons. They're the ones that we can play with. Okay? Now, what's going to basically happen here is on the periodic table, and you've seen the periodic table as we've gone along, on the periodic table, if you go way to the right on the periodic table, and you go to that last column, that last group, because our columns, we call them groups. Groups are the columns, okay, rows are the periods. When we go to that furthest column, we call those the noble gases. And basically, they kind of have found that point where life is good. Okay, it's kind of like when you have those seemingly sometimes rare opportunities to really just sit and enjoy the moment, where maybe you're watching your favorite sporting event, you've got your bowl of chips, you've got your sandwich, you've got your beverage of choice, you've got the remote, no one's home, it's HD TV. Life is good. And there's really not a whole lot other than a natural disaster that's going to get you to move. It's going to get any activity out of you whatsoever. Well, that's the level that those noble gases have reached. And you're like, well, what do they have different than the others? Well, what they have is that outer shell with those valence electrons. Therefore, we call it the valence shell. So that outer shell, whatever the outer shell is for that atom, and I'm going to explain that in a minute, whatever its outer shell is in a situation, the rule is called the octet rule. The goal is to have 8 electrons, okay, if it's a big enough atom, to have 8 electrons in that valence shell. That's what it wants. So if you look at that entire group, except for helium, and I'll explain that, if you look at that entire group on the periodic table as you move down, every one of those elements, again, except for helium, has 8 electrons in its valence shell. Now, the outer shell of that atom may be the second shell. It may be the third shell. It may be it doesn't matter. But the outer shell has 8 electrons in it. So that's what the other elements want to achieve. I mean, who wouldn't want that situation where they're sitting down, life is good, okay, we're enjoying life, those types of things. And so that's what we want to look at. So if we look back at what we're referring to with these valence electrons, you'll notice with hydrogen, which is number 1 on our periodic table. Number 1, the atomic number, meaning the number of protons. Remember, that's what it tells us. And if I have 1 proton, if this is a neutrally charged atom, I need 1 electron. And so that electron exists in that first shell. Now, remember, what does shell number 1 hold? Well, it holds up to 2. So is that shell full? It's not. Okay? Would that shell like to be full? Yes. And what would it like to be full with? Well, it actually would like to be full with 2. Why? Because the first shell holds a maximum of 2. And why also would it like it? Well, remember, if you look at the far group on the periodic table again, the top one being helium. Helium is atomic number 2, which means it has 2 protons, 2 positives. To be neutrally charged, it has to have 2 negatives. Does it have an outer shell that is full? It does. Okay, it has it with 2. Now you're like, well, wait a minute, you told me that it had to have 8. No, it doesn't have to have 8. Okay, it wants to have 8, but remember I said that helium was kind of the exception to that, what we call the octet, or one of the exceptions to that octet rule, or that rule of 8, which is it's satisfied with just a full shell. Does it have a full shell? Yeah, it has 2 electrons. How many does shell number 1 hold? 2 electrons. So hydrogen would like to be full by achieving that same goal. It would like to be like helium. So everybody wants to be like that last group on the periodic table. Notice with oxygen. Oxygen has 8 protons. Therefore, if neutrally charged, it has 8 electrons. It has 2 in the first shell. How do I know that? Because that's the most it can hold. So the first 2 go there. And if I started with 8 and I put 2 in the first shell, well, that leaves me 6 in the next shell. So what would oxygen really like to do? Oxygen would like to beg, borrow, steal, or share. It would like to share 2 more so that it ends up like its noble gas counterparts with 8 in the outer shell. Carbon, atomic number 6, has 6 protons, therefore 6 electrons. 2 electrons in the first shell, 4 in the second shell. What would it like? It would love to have 8. Okay. Therefore, it would like to add 4 more by beg, borrowing, stealing, sharing, whatever it takes. Nitrogen, atomic number 7. Therefore, neutrally charged, 7 electrons, 2 in the first shell, 5 in the second shell. Would love to have 8. Therefore, it would like to add 3 more. So the difference is, very often it says that these shells want to be full. Yeah, it's a little bit scary. Now, in some cases, as we get these smaller elements, that is true. It would like to have 2 in the first shell. Well, that's full. It would like to have 8 in the second shell. Well, that's full. But as we get into the third shell, the fourth shell, whatever, those are getting so big, okay, we truly can't fill them, okay? And so that's where that octet rule comes in, where it wants to look, act, be like, okay, the noble gases in that last column of the periodic table, and where each one has, okay, helium has 2, fills the first shell, 8, 8, 8, 8, 8, 8. The rest of them have 8 in their outer shell. So by saying their shell is full, well, we really need to say, okay, it achieves the octet, or it fills with 8. It's not that it's full. Because you look back at what we calculated the third shell as being. Well, the third shell fills with 18. Oh, that's not 8, okay? But, okay, remember, it feels a little weird when we go from the third to the fourth and the fifth and so on and so forth. Okay? So you can see how each of these are with the ones we're representing on the periodic table. Hydrogen, helium. So hydrogen has 1 in the first shell. Helium has 2. Lithium has 2 in the first shell. Okay, 1 in the last shell, or 1 in the second shell. Now, here comes the question. We're going to get into this a little bit more here as we go along. We got options here. Here with lithium, it has 2 in the first, well, the atomic number is 3. So it has 2 in the first shell. It has 1 in the second shell. So lithium really has options where it says, all right, I can either get rid of an electron, and by doing so, now I have a full first shell, 2. Or I can try to beg, borrow, steal, or share 7 electrons. Well, which one would be easier? Would it be easier to just dump 1 electron or try to assemble 7? Well, it's a heck of a lot easier to dump an electron. So by dumping 1, where there was, okay, an outer shell that didn't have 8 in it, now there's an outer shell that is full, and it's full with 2. And so has lithium, by giving up that electron, has lithium now become like its noble gas counterpart? Yes, it has. Because it had 3, now it has 2. Yeah, so who does it look like? So it looks like helium. As we get out here to fluorine, fluorine, okay, with the atomic number of 9, 2 in the first shell, 7 in the second shell. Oof. Is it easier to try and pass off 7 or just get 1? Well, it's a heck of a lot easier to just get 1. Because who does fluorine want to be like? Well, fluorine wants to be like neon. Neon has 2 in the first shell and 8. There's its rule. Has 8 in the second shell. Okay. As we get further down, look at argon. Argon has 2 in the first shell. Well, why only 2? Because it fills with 2. Then it has 8 in the second shell. And then it has, okay, another 8 in the third shell. But in that valence shell, those valence electrons, it again achieves its octet. So chlorine and sulfur would love to look like, act like, be like argon. So they're all trying to achieve either that full first shell or achieve an octet, okay, which is having 8. And so there are options, and there are options that are easier than others. Now, not to say they can't do it the other way, but there are options that are a little easier. So oxygen, which has 6, would like to gain 2 electrons rather than try to lose 6. Okay, hydrogen would like to either get rid of an electron, and we'll talk about that, okay, or gain an electron to get 2. Okay, carbon would like to give away 4 or get 4, and that's where it becomes so versatile. And we're in our next module, we're going to talk a great deal about why that versatility becomes so important to us. Nitrogen, do I want to gain 3 or get rid of 5? Well, gaining 3 is a little easier than getting rid of 5. Okay? And so we essentially want to be like those noble gases. So just be careful, because very often in references it talks about filling the outer shell. There's a difference between filling it with the maximum number that it can have or filling it with and achieving the octet, or achieving those 8 electrons to be like those noble gases. So just be aware of that as we look at it. So for example, let's look at magnesium, because it's one we deal with in our body. It plays a big role in a lot of chemical reactions in our body. So magnesium, which is atomic number is 12, it has then, let's distribute them, okay, and be able to do this. So we have 12 electrons. There's going to be, how many in the first shell? 2. Okay, so now I'm down to 10. How many in the next shell? Well, it fills with 8, so I'm going to put 8 there. So I put 2 in the first, I put 8 in the second, okay, so I've used 10 of my 12. So what does that mean is in that third shell? Well, there are 2 that are there. So again, magnesium would like to have 8 in its outer shell, okay, and maybe I should draw this and see if this makes it a little easier to visualize rather than, even though, okay, it doesn't take too long to learn, okay, my abilities as a graphic artist. All right, so we're looking at magnesium, okay, and this is a very important principle as we understand what these things called ions are and electrolytes are and some of those things. All right, so in the nucleus with magnesium being the atomic number 12, what does that tell me? That means there are 12 protons there. I then have, to be neutrally charged, I have 12 electrons hanging out somewhere. So I just have to distribute them amongst the shells. So in the shells, I of course have 2 in the first shell. Now notice I drew them together. Hold on to that thought. Then in the second shell, I have, because it fills with, okay, again, why in the first shell are there 2? Because it fills with 2. Next one, okay, there's 8, and it fills with 8. So I've got 2 here, I've got 8 here. So of these 12, so far I have used 10. That leaves me 2 electrons to deal with. So that means in the third shell, there are 2 electrons hanging out here. Okay, so here's the option. The option is I have 2 in the outer shell. Therefore, do I want to add 6 to get to my 8, or do I want to minus those 2 to get to my 8? You're like, well, wait a minute. I can understand by adding 6 how I'm going to get to my 8. But how does minusing 2 get to my 8? Well, watch this. What if these disappeared? Doesn't that essentially get rid of the third shell? Because there's nothing there. So there's really not a third shell. So therefore, what does it leave me? 2, 4, 6, 8 in the what is now the outer shell. So if I achieve that, I end up having 12 protons, because that's what makes it magnesium, and I have 10 electrons. Now they're not equal, so therefore that atom is not neutrally charged, okay, and that will come into play, okay, coming up in a forthcoming objective. Okay, but that's what takes place in that process of how we're filling shells, we're filling them with 8, okay, to achieve that octet. We are not filling them to their maximum capacity, because, okay, that gets kind of crazy big, okay, in terms of that process.